Hi, and welcome to Computing Fundamentals 2. In last video, we have defined and discussed what do we mean by trees in computing. In this video, we will focus on the following topics. Binary search trees, which is one of the most efficient techniques we use to find an element in a list or a database. Let's say we want to search for a student from a student database, whereas his first name is Ben, for example. We use binary search tree to query a database and return a result in a very efficient time. Also, we are going to discuss decision trees, which they are used very heavily in data analytics and data mining, as we are going to see in this video. In addition to that, we will discuss prefix codes and Huffman coding as an effective technique for encoding a string using the fewest possible bits. But first, I want you to review a few theorems from the last video before we start taking those new concepts and discussing them. A tree is a connected and directed graph with no simple circuits. Because a tree cannot have a simple circuit, a tree cannot contain multiple edges or loops. Therefore, any tree must be a simple graph. A full emery tree with I internal vertices contains n, which basically equals to the m multiplied by I plus 1. So this is basically where m equals to the degree of the tree. So for example, a binary tree, m equals to 2, and I is basically equals the number of internal vertices in the tree. So the total number of vertices in this tree, n, equal m multiplied by I plus 1. Also, we have another theorem to discuss, and we call it corollary 1. A corollary 1 telling us a full emery tree with m degree of the tree, we have n vertices, which has I, the internal vertices, equals to n minus 1 divided by m. And also m in this case equals the degree of the tree. And L, which basically refers to the number of leaves in the tree, equal the absolute value of m minus 1 multiplied by n plus 1 divided by m, and this is basically giving us the number of leaves in the tree. I, which is internal vertices, has n equal m multiplied by I plus 1 vertices, and L equal m minus 1 multiplied by I plus 1 leaves. L leaves has an n equal to m multiplied by L minus 1 divided by m minus 1 vertices, and I equal L minus 1 divided by m minus 1 internal vertices. We have discussed this corollary in the last video. But we will discuss the three problems that can be studied using trees. So the first problem is, how should items in a list be sorted so that an item can be easily located? The second problem is, what series of decisions should be made to find an object with a certain property in a collection of objects of certain type? The third problem is, how should a set of characters be efficiently coded by bit strings? So first, let us start by discussing binary search trees. Searching for items in a list is one of the most important tasks that arises in computer science. Our primary goal is to implement a searching algorithm that finds items efficiently when the items are totally ordered. This can be accomplished through the use of binary search tree, which is a binary tree in which each child of a vertex is designated as a right or left child. No vertex has more than one right child or left child, and each vertex is labeled with a key, which is one of the items. Review last video to understand more about the tree structure and the definition of a tree. Furthermore, vertices are assigned keys so that the key of a vertex is both larger than the keys of all vertices in its left subtree and smaller than the keys of all vertices in its right subtree. This recursive procedure is used to form the binary search tree for a list of items. Start with a tree containing just one vertex, namely the root. The first item in the list is assigned as the key of the root. To add a new item, first you need to compare it with the keys of vertices already on the tree, starting at the root and moving to the left or to the right based on the value of this new child. If the item is less than the key of the respective vertex, if this vertex has a left child, or moving to the right if the item is greater than the key of the respective vertex if this vertex has a right child. When the item is less than the respective vertex and this vertex has no left child, then a new vertex with this item as its key is inserted as a new left child. In similar way, when the item is greater than the respective vertex and this vertex has no right child, then a new vertex with this item as its key is inserted as a new right child. In similar way, when the item is greater than the respective vertex and this vertex has no right child, then a new vertex with this item as its key is inserted as a new right child. In example 1, we need to form a binary search tree for the words mathematics, physics, geography, zoology, meteorology, geology, and physiology, and chemistry, using alphabetic order. Figure 1 displays the steps we use to construct this binary search tree. The word mathematics is the key of the root. Because physics comes after mathematics in alphabetical order, we add physics to the right child of the root with key physics. Because geography comes before mathematics, we add it to the left child of the root and with the key geography. Next, add a right child of the vertex with the key physics and assign it the key zoology, because zoology comes after mathematics and after physics. In the similar way, add a left child of the vertex with the key physics and assign this new vertex the key meteorology. Add a right child of the vertex with key geography and assign this new vertex the key geology. Add a left child of the vertex with key zoology and assign it the key physiology. Add a left child of the vertex with key geography and assign it the key chemistry. The viewer should walk through all the comparisons needed at each step. Once we have a binary search tree, we need a way to locate items in the binary search tree, as well as way to add new items. Algorithm 1, an insertion algorithm, actually does both of these tasks, even though it may appear that it is only designated to add vertices to a binary search tree. That is, algorithm 1 is a procedure that locates an item X in a binary search tree if it's present and adds a new vertex with X as its key if X is not present. In the pseudocode, V is the vertex currently under examination and label of V represents the key of this vertex. The algorithm begins by examining the root if X equals the key of V. Then the algorithm has found the location of X and terminates if X is less than the key of V, and we move to the left child of V and repeat the procedure. And if X is greater than the key of V, we move to the right child of V and we repeat the procedure. If at any step we attempt to move to a child that is not present in the tree, we know that X is not present in the tree, and we add a new vertex as this child with X as its key. Example 2 illustrates the use of algorithm 1 to insert a new item into a binary search tree. Use algorithm 1 to insert the word oceanography into the binary search tree in example 1. Algorithm 1 begins with v, the vertex under examination, equal to the root of t. So label of v equal mathematics, because v not equal null, and label of v equal mathematics, which is basically less than oceanography. We next examine the right child of the root. The root child exists, so we set v, the vertex under examination, to be this right child. At this step, we have v not equal null and label of v equal physics. And physics is greater than oceanography, so we examine the left child of v. This left child exists, so we set v, the vertex under examination, to this left child. At this step, we also have v not equal null and label of v equal metrology, which less than oceanography, so we try to examine the right child of v. However, this right child does not exist, so we add a new vertex as the right child of v, which at this point is the vertex with key meteorology, and we set v equal to null. We now exit the while loop because v equal null, because the root of t is not null and v equal null, and we use the else if statement at the end of the algorithm to label our new vertex with the key oceanography. We will now determine the computational complexity of this procedure. Suppose we have a binary search tree for a list of n items. We can form a full binary tree U from T by adding unlabeled vertices whenever necessary, so that every vertex with a key has two children. This is illustrated in figure 2. Once we have done this, we can easily locate or add a new item as a key without adding a vertex. The most comparisons needed to add a new item is the length of the longest path in U from the root to a leaf. The internal vertices of U are the vertices of T. It follows that U has n internal vertices. We can now use part 2 of theorem 4 to conclude that U has n plus 1 leaves. Using corollary 1 of a previous section, we see that the height of U is greater than or equal to h, where h equal log n plus 1. It is necessary to perform at least log n plus 1 comparisons to add some item. Note that if U is balanced, its height is log n plus 1 by corollary 1 of the previous section. Thus, a binary search tree is balanced. Locating or adding an item requires no more than log of n plus 1 comparisons. A binary search tree can become unbalanced as items are added to it. Because balanced binary search tree give optimal worst case complexity for binary searching, algorithms have been devised that rebalance binary search tree as items are added. The interested reader can consult references on data structures for the description of such algorithms. Thank you for